Good morning, everyone. My name is JianWang from Wuhan University, China. I'm really sorry that I cannot be present at this conference because I still haven't get my visa to Cyprus until now. Many thanks for the program chair, Georgia, to allow me to present our work using this video. The title of our work is An Approach for Prioritizing Software Features based on Node Centrality in Probability Network. Firstly, I want to introduce some background knowledge. Our work is closely related to the field of requirements prioritization. Faced with the increasing complexity of software products as well as the restriction of the development budget and time, how to select the crucial software requirements to be preferentially developed becomes increasingly important for the success of software products. Currently, many requirements prioritization approaches have been proposed. Most of these approaches consider more on requirements attributes. For example, the values, cost, risk of the requirements. And most of these approaches neglect the dependencies between requirements. Features are closely related to requirements. According to the definition of IEEE, a feature is defined as a software characteristic specified by requirements documents. Therefore, we argue that feature prioritization can contribute to requirements prioritization. Existing works on feature models mainly focus on feature selection in the derivation of feature model configurations. In Harry's work, they firstly introduced the concept of feature prioritization and proposed an approach named SAHP to rank and select the most relevant features from the feature model, aimed at an automated derivation of specific software products by associating stakeholders' business requirements with features. In their work, they did not consider the structure of feature models. Therefore, the problem to be solved in our work is how to leverage the structure of feature models in feature prioritization. The basic solution is to generate feature probability networks for feature models. And we then measure the node centrality in the probability network to rank the priority of each features. This is the overall framework of software feature prioritization. The input of our framework is software feature models. In our framework, the first step is to generate a feature probability network. Based on the generated feature probability network, we can measure the node centrality of each feature in the network, and which could be viewed as the priority of each features. And this feature prioritization result can be used to guide the requirements prioritization. As we have mentioned, the input of our framework is feature models. I think that every audience of this conference are very familiar with feature models, so we don't introduce more about the definition of feature models. This figure shows an example feature model on text editor. It is depicted according to a feature model registered in Sprout. We know that Sprout is a famous publicly available feature model repository. With this feature model, we can see that the root feature is text editor. It consists of two mandatory sub-features, text editing and file operations. we can see from this model that it still have many different kinds of relationships between features besides the mandatory relation. It has optional, XOR, requires, excludes, and these different kinds of relations will be considered in our approach. Then we will discuss how to generate a feature probability network. Firstly, we need to generate nodes. In our approach, each feature in the feature models will be a node in the feature probability network. Secondly, we need to generate the edges between each nodes. We will consider the following cases. Firstly, if a feature I is a parent feature of feature J in the feature model, there will be bidirectional edges between nodes I and J in the feature probability network. In the second case, if feature I is an ancestor feature of feature J in the feature model, there will also be bidirectional edges between these two nodes. In the third case, if feature I requires feature J in feature models, there will be a directed edge from node I to node J in the feature probability network. Otherwise, there will be no connection between feature I and J in the feature probability network. Finally, we will discuss how to generate weights on edges. Firstly, if there is no edge from I to J, the weights between I and J will be 0. Secondly, if feature I is a parent feature of feature J in the feature models, the weight of the edge from J to I will be 1. But for the weight of the edge from I to J, there will be different. We will consider the following 4 cases according to the relationship between I and J. If there is a mandatory relation, the weight of the edge from I to J will be 1. If there is an optional relation, the weight of the edge from I to J will be 0.5. If there is an XOR relation, the weight of the edge from I to J will be 1 divided by G, where G is the number of features that share the same parent feature with J by XOR. If there is an OR relation, the weight of the edge from I to J will be a random number from between 1 divided by G to 1. In the third case, if feature I is an ancestor feature of J in the feature model, the weight of the edge from J to I will be 1. But the weight of the edge from I to J will be the multiplication of the weights of each edge from I to J. In the fourth case, if feature I requires J in feature models, the weight of the edge from I to J will be 1. In this way, we can generate the weights on the edges in the feature probability network. Based on the generated feature probability network, we can calculate the node centrality of each node in the network. For each node I in the network, we firstly calculate its in degree and out degree. The in degree is defined as the input width of the node, and the out degree is defined as the output weights of the node. The node centrality of each node is defined as the combination of the in degree and out degree using the equation 14. Clearly, the node centrality will increase with the increase of its in degree and the decrease of its out degree. In our work, the node centrality is viewed as the priority values of each feature in the feature models. This figure shows the generated feature probability network of the example feature models mentioned above. The first figure is a network, and the second figure is a weighted matrix in the feature probability network. And the third tables shows the values of the in degree, out degree, and node centrality of each feature. This algorithm shows the whole process of our feature prioritization approach. The input of the algorithm is a software feature model, and the output will be a priority ranking list of features. The steps just follow what we have mentioned just now. We firstly copy the nodes in the feature model to the network and generate the edges and the weights of the network. And then we will calculate the in degree, out degree, and the node centrality of each node. And we also use the relationships of requires and excludes to sort the orders of the features. The time complexity of the algorithm is O n squares. Then we will discuss the evaluation part of our approach. In the evaluation part, we selected 3 feature models from the Splot repository. They are text editor, help system, software stack. These 3 feature models are not very large. The number of the features in these 3 models are 12, 25, and 37 respectively. These feature models consist of different kinds of feature relations, including elementary, optional, all, XOR, requires, excludes. Because the Splot dataset did not provide any information on the priority between features, we have to build the ground truth manually. The building process is similar to the AHP method. Firstly, a table for each feature model is created to record the priority comparison result. Then a small group meetings participated by 2 PhD students and 3 master students are held. And these participants are requested to fill in the tables, and they discussed and negotiated with the inconsistent results. And finally, the priority scores of each feature will be ranked. In our evaluation part, we need to answer 2 research questions. The first question is about whether the proposed approach can accurately predict the priority between features in their feature models. The second problem is about whether the execution time of the proposed approach is acceptable. In order to answer the 2 research questions, we need to define some evaluation indicators. The first one is Spearman's rank correlation coefficient. It is used to measure the statistical dependence between the proposed approach and the ground truth. The second one is accuracy. Accuracy is defined based on the values of the disagreement, where disagreement refers to the total number of inconsistent priority comparison for each feature pairwise between the proposed approach and the ground truth. These two indicators are used to evaluate the first questions, while for the second question we use execution time. Okay, this table shows the results of the first research questions. According to this table, we can see that the number of feature pairs in these three models are 66, 300, 600, and 66 respectively. Among these feature pairwise, the disagreements between the proposed approach and the ground truth is 8, 25, and 49 respectively. And we can see that the accuracy is around 90%. As for the Spearman's rank correlation coefficient, they are about 90%, which implies that the proposed approach and the ground truth are closely related. This figure shows the change trend of the execution time of the proposed approach. Because the scale of the three selected feature models are not very large, besides these three models, we also generate some feature models according to the feature model editor in Splot. The feature number of these generated feature models are from 50 to 200. According to this figure, we can see that the execution time grows nearly in a trend no more than O(n squared) with the increase of the number of features. We think that this kind of execution time is acceptable for the feature prioritization. Okay, that's the results of our approach. As for the threats to validity, we think that our approach only considers the priority between features from the structure of the feature models. There are also other factors that can influence the priority of features, such as stakeholder preferences, costs, and risks, and so on. Anyway, we think that our approach just provides a complementary view for feature or requirements prioritization. There are also many other threats to validity, such as the scale of the feature models and the authority of determining the ground truth. We have tried our best to mitigate the threats to validity. Finally, we summarize our work. In our work, we propose a method of generating the feature probability network from the feature models, and we propose a measurement method for node centrality to calculate the priority of features. We also conducted experiments on 3 real feature models to evaluate the proposed approach. In future, we plan to extend our work from the two aspects. Firstly, we will combine the proposed approach with automated reasoning methods to support feature model configuration, and we then evaluate the performance of our approach when the feature number grows to a very large scale. Okay, that's all. Thank you.